Jupiter looks calm from millions of miles away, but beneath its swirling clouds lies a world far stranger than scientists expected. NASA's Juno spacecraft has been peering through that violent atmosphere, revealing enormous storms, powerful magnetic fields, and clues that Jupiter's hidden interior may not look anything like the models predicted. Tonight we follow Juno beneath the clouds and explore what it actually discovered inside the solar system's largest planet. If you enjoy calm journeys through the mysteries of space, please like the video, subscribe to the channel, and settle in as we begin. Juno approaches Jupiter along a long, narrow orbit that carries the spacecraft over the planet. Spacecraft do not obtain from orbit. Most of each circuit unfolds far from the planet, where Jupiter appears as a bright banded globe suspended against dark space. The spacecraft then falls inward under Jupiter's gravity, gathers speed, and passes close above the cloud tops before climbing outward again. The closest point is called perigove. The farthest point is called apogee. Together, these two parts of the orbit create a repeating rhythm of distant preparation and brief, concentrated observation. The orbit is strongly elliptical, meaning that it is stretched rather than circular. During much of the mission, one circuit lasts about 53 days. Gravitational encounters with Ganymede, Europa, and Io shorten the period, and by early 2024, the orbit lasts about 33 days. At its closest, Juno passes roughly 3,500 kilometers above Jupiter's visible clouds. At the far end of its path, it travels millions of kilometers away. This broad swing limits the time spent in the most intense radiation, while still allowing close measurements. Juno moves from pole to pole during each close passage. Jupiter rotates rapidly beneath it, completing one turn in a little less than 10 hours. Because the spacecraft crosses northern latitudes, the equator, and southern latitudes while the planet turns below, repeated passes gradually place different longitudes under its instruments. The orbit acts as a moving line of observation across a rotating world. It does not remain above one fixed region. It gathers narrow strips of information that scientists later combine into wider maps. The spacecraft is spin-stabilized. Its central body turns about twice each minute during normal science operations. This steady rotation keeps its orientation stable without requiring constant pointing adjustments. Most instruments are fixed to the spacecraft rather than mounted on moving platforms. As Juno spins, their fields of view sweep repeatedly across space and Jupiter. Each rotation produces another measured arc. During a close passage, these arcs overlap and form a detailed record of changing position, brightness, energy, particles, and fields. 3 large solar arrays extend from the central body. Together, they give Juno a broad 3-bladed form. Sunlight near Jupiter is much weaker than sunlight near Earth, so the arrays cover a large area and remain directed to receive as much light as possible. The polar orbit and spacecraft orientation help keep them illuminated. Solar power supports the instruments, computers, heaters, communication systems, and careful control needed during each encounter. Jupiter surrounds itself with a severe radiation environment. Fast electrons and ions can damage electronics, disturb detectors, and slowly weaken materials. Juno's path avoids the strongest regions for much of each orbit, but every close approach still brings substantial exposure. The spacecraft protects many sensitive systems inside a thick titanium vault near its center. This enclosure does not stop all radiation. It reduces the dose enough for the electronics to continue working through repeated passages. Instrument design, orbit design, shielding, and limited close-pass duration all support that protection. Juno's measurements begin with geometry. Scientists determine the spacecraft's position, speed, and orientation with great precision. Radio signals pass between Juno and antennas of NASA's Deep Space Network on Earth. Small changes in the frequency of the returning signal reveal changes in the spacecraft's motion. Jupiter's gravity slightly accelerates or slows Juno as it passes over regions with different distributions of mass. The radio link therefore serves as a gravity instrument, even though no separate gravity sensor extends from the spacecraft. A pair of magnetometer sensors measures the strength and direction of the magnetic field. They are mounted away from the spacecraft body on one solar array so that electrical activity from the spacecraft interferes as little as possible. Star cameras near the sensors determine their exact orientation by observing the surrounding stars. The combination allows the magnetic measurements to be placed accurately in space. Other instruments examine particles and waves around the spacecraft. The Jovian Auroral Distributions Experiment measures lower energy electrons and ions. The Jupiter Energetic Particle Detector instrument measures particles at higher energies. The WAVES instrument records electric and magnetic fluctuations in the surrounding plasma, which is a thin gas containing electrically charged particles. These instruments describe the environment through which Juno moves and show how energy travels around the planet. Remote sensing instruments observe Jupiter without touching its atmosphere. The ultraviolet imaging spectrograph records ultraviolet emissions. The Jovian Infrared Auroral Mapper detects infrared energy and produces temperature-sensitive views. JunoCam records visible light showing cloud forms and broad color patterns. The Stellar Reference Unit, designed mainly for navigation, also collects faint images under low-light conditions. Each instrument receives a different part of the energy arriving from Jupiter, so its record describes a different physical property. The microwave radiometer consists of 6 antennas that measure naturally emitted microwave energy across several wavelength ranges. Microwaves can emerge from levels hidden below the visible clouds, because they pass through some atmospheric material more readily than visible light. The instrument does not take an ordinary photograph. It measures brightness related to temperature and composition along each viewing path. Spacecraft rotation sweeps the antennas across Jupiter, producing bands of microwave data that can be compared from one close pass to another. Juno's observing system depends on the agreement of many measurements rather than on a single image or detector. Position data establish where the spacecraft is. Timing data establish when each reading occurs. Orientation data establish where each instrument points. Calibration corrects for known behavior within the sensors. Scientists align radiomagnetic particle wave, ultraviolet infrared visible, and microwave records within a common spatial framework. A close pass from north to south takes only a few hours, and the most concentrated observations occur near perigove. During that interval, Juno travels rapidly relative to Jupiter. Instruments collect information in carefully planned sequences while the spacecraft continues its steady spin. Data are stored on board and transmitted to Earth over time, often when Juno is farther from the planet and immediate observational demands are lower. This polar measuring path turns motion into a scientific tool. The long orbit controls radiation exposure and solar illumination. The close approach strengthens gravity, magnetic, atmospheric, and imaging signals. The pole-to-pole direction covers every latitude. Jupiter's rotation changes the longitude beneath each pass. Juno's own rotation sweeps fixed instruments across their targets. The result is a coordinated method for examining a planet whose visible clouds conceal most of its mass, energy, and structure. Above Jupiter's poles, Juno enters a region shaped less by clouds than by magnetic force. The planet's magnetic field extends far into space and controls the motion of electrically charged particles around it. This broad region is called the magnetosphere. It is not empty. It contains electrons, ions, thin plasma electric currents, and waves that respond to Jupiter's rotation and to material supplied by the moon Io. Near the poles, magnetic field lines guide some of this material toward the upper atmosphere, while other particles move outward or circle the planet in large changing paths. Jupiter's magnetosphere is the largest known structure produced by a planet. On the side facing the Sun, the solar wind presses against it and compresses its boundary. On the night side, the magnetic field stretches far behind the planet. Juno's polar orbit does not remain near the flat middle region, where many trapped particles circulate. It passes above high latitudes where magnetic field lines bend steeply and connect distant parts of the magnetosphere to the atmosphere below. The magnetic field near Jupiter is much stronger than Earth's field. Its axis is tilted relative to the planet's rotation axis, and its shape is uneven. Juno's magnetometers record changes in strength and direction as the spacecraft crosses different magnetic regions. The measurements show that the field is not a simple dipole, which is the basic pattern produced by a bar magnet. Instead, some areas are stronger, some are weaker, and the field contains local features that affect how particles travel. As Jupiter rotates in less than 10 hours, its magnetic field rotates with it. This rapid motion influences the surrounding plasma and encourages much of it to move around the planet. The plasma does not always keep the same speed as Jupiter's deep interior. Differences in motion create electric currents and stresses within the magnetic environment. These currents can transfer energy across great distances without requiring solid matter to carry it. Io plays an important role in this system. Volcanoes on its surface release gases containing sulfur and oxygen. Much of this material escapes into space and becomes electrically charged. The resulting plasma forms a broad torus around Jupiter near Io's orbit. Jupiter's magnetic field captures much of it and carries it around the planet. Some particles gradually move inward, while others move outward. Their paths are altered by electric fields, magnetic forces, collisions, and waves. Near the poles, Juno measures particles that travel along magnetic field lines, rather than mainly around the planet. Electrons and ions can move downward toward Jupiter or upward away from it. The Jovian auroral distributions experiment separates these particles by their energy direction and type. The Jupiter Energetic Particle Detector instrument measures more energetic populations. Together, these records show that the polar environment contains several particle groups moving in different directions at the same time. One important finding is that Jupiter's auroral particle acceleration does not follow one simple pattern. At Earth, strong auroral displays often involve electric potentials that accelerate electrons downward along magnetic field lines. Similar structures exist at Jupiter, but Juno also detects broad regions where particles gain energy through turbulent processes and wave activity. Some electrons form beams, others show wide energy distributions. Some ions move upward from the planet, indicating that the upper atmosphere can also supply material to the magnetosphere. The WAVES instrument listens to the electric and magnetic disturbances produced within the plasma. These disturbances are not sound in ordinary air. They are changing fields that travel through charged particles and can exchange energy with them. Juno detects radio emissions, Whistler mode waves, and other plasma signals near the poles. Their frequencies and intensities help identify the local particle conditions and the processes that guide or accelerate them. Jupiter produces powerful radio emissions because fast electrons move through its magnetic environment. Some of these emissions are linked to the polar regions and to auroral activity. The radio energy can be strongly directed rather than spread equally in all directions. As Juno changes position, the spacecraft sometimes crosses narrow zones, where these emissions become intense and then fade. The changing signal reveals the geometry of the source and the motion of the particles producing it. The polar magnetosphere is also divided by boundaries. Juno crosses regions where the direction of particle motion, electric current, or magnetic connection changes. Some field lines connect to the inner magnetosphere where plasma rotates with Jupiter. Others reach into more distant space. The transition between these systems can shift with solar wind pressure, internal plasma supply, and Jupiter's rotation. Electric currents flow along magnetic field lines between the magnetosphere and the atmosphere. These are called field-aligned currents because they follow the direction of the magnetic field. Juno's magnetometers identify them through small changes in the surrounding field. Their arrangement near Jupiter is complex. Some currents carry energy downward, while others complete return paths upward. Their distribution differs between the northern and southern polar regions because Jupiter's magnetic field is not symmetrical. Juno also finds that the polar regions contain energetic ions with compositions that help trace their origins. Some come from Eo's sulfur and oxygen. Others may include protons from hydrogen. Their energy and direction show how material circulates and escapes. The measurements indicate that Jupiter's magnetosphere is not a closed container. It continually exchanges matter and energy with its moons, the solar wind and the upper atmosphere. The solar wind still influences this vast system, even though Jupiter's rotation supplies much of its internal energy. Changes in pressure from the Sun can compress the magnetosphere and alter currents, particle motion, and auroral power. Juno's measurements sometimes show responses to these external changes, but the exact relationship is difficult to isolate because the magnetosphere also changes through its own internal processes. Across repeated polar passes, Juno builds a moving record of magnetic structure, particle flow, and plasma waves. The measurements show a magnetosphere driven by rapid rotation, fed by volcanic material, disturbed by the solar wind, and linked to the atmosphere through electric currents. Above the poles, energy moves along invisible paths that are traced only through the particles' waves and magnetic changes recorded during each passage. At the upper edge of Jupiter's atmosphere, the gas becomes extremely thin, yet it remains active. This region includes the thermosphere, a high layer, where sparse particles can reach high temperatures, and the ionosphere, a partly overlapping layer where sunlight and energetic particles remove electrons from atoms and molecules. Near the poles, these layers receive a continuing flow of energy from the magnetosphere. Juno observes the result through ultraviolet light-infrared emission, charged particles, radio waves, and changes in the surrounding magnetic field. Most of Jupiter's upper atmosphere consists of hydrogen. Molecular hydrogen contains pairs of hydrogen atoms bound together. Helium is also present with smaller amounts of methane and other gases. When energetic electrons descend along magnetic field lines, they collide with hydrogen molecules. The collisions can raise the molecules into excited states. As the molecules return to lower energy states, they release ultraviolet light. This glow forms much of Jupiter's aurora and allows the path of incoming energy to become visible. Juno's ultraviolet spectrograph records this light while the spacecraft passes above the poles. The instrument separates ultraviolet radiation by wavelength, allowing scientists to distinguish patterns linked to different energies and atmospheric depths. Bright arcs, narrow streaks, diffuse patches, and moving spots appear within the polar emissions. These forms do not behave as fixed markings. Their brightness and position change as particle flows and electrical conditions vary above the atmosphere. The main auroral oval forms a broad ring around each magnetic pole. It marks a region where powerful currents connect the upper atmosphere with the rotating magnetosphere. The oval is not centered perfectly on the geographic pole because Jupiter's magnetic field is tilted and uneven. Its shape is also different in the north and south. Juno's close polar view reveals structures that are difficult to see from Earth, especially across the southern polar region. Within the main oval, the aurora contains fine details that change over short periods. Some emissions arise from concentrated electron beams, others are produced by broader groups of particles with a wide range of energies. Juno measures the particles above the glow and compares their motion with the ultraviolet light below. The relationship is not always simple. A strong particle beam can produce a narrow, bright feature, while turbulent acceleration can create a more spread-out emission. Different processes can operate close together. The color recorded by the ultraviolet instrument is not color visible to human eyes. It represents measured wavelengths and intensities. Some ultraviolet wavelengths are absorbed more strongly by methane in the upper atmosphere. This absorption helps estimate how deeply the incoming electrons penetrate. More energetic electrons can reach denser gas at lower altitudes before losing their energy. Less energetic electrons release most of their energy higher above the planet. The observed spectrum therefore provides a rough measure of particle energy and the depth of atmospheric interaction. The collisions do more than create light. They ionize molecules by removing electrons, forming positively charged ions and free electrons. They can also separate molecular hydrogen into individual atoms. Repeated collisions warm the surrounding gas and alter its chemistry. The ionosphere becomes a changing electrical layer whose density depends on sunlight, auroral particles, chemical reactions, and transport by winds. Near the poles, particle precipitation can produce dense local regions of ionization. Jupiter's upper atmosphere is much hotter than heating by sunlight alone can explain. Auroral energy contributes substantially to this high temperature. Incoming particles deposit heat directly, while electric currents produce additional heating. When charged particles move through the partly ionized atmosphere, collisions with neutral gas resist their motion. This process converts electrical energy into heat and is often called Joule heating. The effect is strongest where currents and electric fields are intense. Juno's magnetic and particle measurements help locate these energy inputs, while infrared observations show part of their atmospheric response. The Jovian infrared auroral mapper detects infrared emission from a charged form of hydrogen made from 3 hydrogen nuclei. This ion, called trihydrogen, forms in the ionosphere after molecular hydrogen is ionized and reacts with more hydrogen. Its infrared glow provides information about temperature, density, and motion in the auroral upper atmosphere. Trihydrogen does not survive equally well everywhere. Its abundance depends on chemical reactions and the presence of other molecules. In some regions it emits strongly, while in others it becomes weak, even when energy continues to enter the atmosphere. Infrared brightness, therefore, does not measure temperature alone. Scientists compare it with ultraviolet emissions, particle data, and magnetic measurements to separate changes in heat from changes in composition. The upper atmosphere also responds through winds. Strong heating near the auroral zones creates pressure differences that can drive gas away from the poles. Jupiter's rapid rotation influences this motion and tends to turn moving air sideways. Ionized particles are also tied partly to the magnetic field, while neutral molecules are not. Collisions between the two populations transfer momentum, creating a complex pattern of winds and electrical drag. Observations indicate that auroral heating can spread beyond the immediate polar source. Warm gas and waves carry energy toward lower latitudes, although the efficiency and timing vary. Jupiter's upper atmosphere does not behave as a set of isolated layers. Neutral winds, ions, electrons, magnetic forces, and radiation interact continuously. It remains uncertain how each process contributes during every change in auroral activity, because Juno samples only limited paths while the atmosphere continues to evolve. Several smaller auroral features record direct connections with Jupiter's large moons. Io, Europa, Ganymede, and Callisto disturb the magnetic plasma through which they move. These disturbances travel along magnetic field lines and reach Jupiter's upper atmosphere, where they create compact emissions and trailing patterns. The locations of these features shift with the Moon's orbital positions and with changes in the surrounding plasma. Juno's measurements show that Jupiter's auroral upper atmosphere is both a luminous boundary and an active energy processing region. Molecular hydrogen receives energy, releases ultraviolet light, becomes ionized, and participates in changing chemical reactions. Electrical currents add heat. Infrared emitting ions trace parts of the temperature and circulation. Winds redistribute energy, while the planet's rotation and magnetic field shape their movement. Across the polar thermosphere and ionosphere, the atmosphere converts invisible flows of charged particles into light-heat motion and altered chemistry. Below the glowing upper atmosphere, Jupiter's gas becomes denser and quieter in appearance, though it remains in constant motion. This region is the stratosphere, a broad atmospheric layer above the main visible clouds. It contains very little water condensation and almost no weather in the familiar terrestrial sense, yet it holds thin hazes, chemical products waves, and weak temperature changes that preserve the influence of sunlight, auroral energy and circulation from deeper levels. The stratosphere begins above the main ammonia cloud deck and extends upward through pressures far lower than those near the visible cloud tops. Hydrogen and helium still dominate the gas. Methane, ammonia, acetylene, ethane, and other minor compounds occur in much smaller amounts. These trace gases absorb sunlight, react with energetic particles, and form new molecules. Some of the products gather into tiny solid or liquid particles that remain suspended for long periods. These suspended particles create Jupiter's high hazes. A haze differs from a cloud mainly in the size, origin, and concentration of its particles. Clouds form when a gas condenses into larger droplets or crystals under suitable temperature and pressure. Haze particles are often smaller and may form through chemical reactions driven by ultraviolet sunlight. Their small size allows them to remain aloft, carried by weak vertical motion and broad horizontal winds. At low and middle latitudes, the haze appears as a thin veil above the more sharply defined cloud bands. Near the poles, it becomes thicker, more layered and more strongly shaped by circulation. Images from Juno show pale bluish and reddish veils spread across the polar regions. Some appear smooth, while others contain narrow bands, arcs, and folded structures. These forms reveal movement within a layer that otherwise lacks the strong color and contrast of the clouds below. Sunlight begins the main chemical process. Ultraviolet radiation breaks methane molecules into smaller fragments. These fragments combine into hydrocarbons such as acetylene and ethane. Further reactions produce more complex molecules that can condense into particles. The exact composition of the haze remains uncertain because the particles are extremely small and difficult to sample remotely. Observations indicate that hydrocarbons are important, while compounds containing nitrogen, sulfur, or phosphorus may also contribute in some regions. Auroral activity changes the chemistry near the poles. Energetic particles enter from above and strike methane, molecular hydrogen, and other gases. These impacts break molecular bonds and create reactive fragments. The products can follow chemical paths that differ from those driven by sunlight alone. Some new molecules absorb blue or ultraviolet light, giving parts of the polar haze a reddish or brownish tone. The color varies with altitude, particle size, composition, and the amount of material along the line of sight. Juno's visible camera records the haze mainly through differences in brightness and color. Sunlight scattered by small particles produces soft, diffuse features. The viewing angle matters strongly. When sunlight passes through a long path near the edge of the planet, a very thin layer can appear bright. When the same layer is viewed from above, it may look faint. Repeated passes from different positions help separate true changes in the haze from changes caused by lighting. Infrared measurements provide another view. The Jovian infrared auroral mapper detects heat radiation and reflected sunlight across selected wavelengths. Some wavelengths pass through haze more easily, while others are absorbed or scattered. This contrast helps identify altitude differences and particle properties. Warmer regions emit more strongly in parts of the infrared, while chemical gases leave narrow absorption features. Together, these signals reveal a layered atmosphere rather than a single uniform veil. Temperature in the stratosphere generally rises with altitude because methane absorbs sunlight. The increase is modest compared with the hot thermosphere above, but it affects where gases condense and where haze particles form. Small temperature changes can shift the altitude at which a compound becomes solid or liquid. They can also change reaction rates and the speed at which particles settle. The polar stratosphere is influenced by large-scale circulation. Air can rise from deeper levels, spread horizontally, and sink elsewhere. Rising motion carries trace gases and freshly formed particles upward. Sinking motion brings chemically altered material downward. Jupiter's rapid rotation turns these flows and helps organize them into broad bands and vortices. The resulting circulation is slow compared with the fast cloud-top winds, yet it shapes the haze over months and years. Waves also pass through the stratosphere. Some begin in storms and turbulent motions below, then travel upward through the gas. As the atmosphere becomes thinner, the waves can grow in amplitude. They produce small changes in temperature, density, and wind. Repeated wave activity can move energy and momentum through the haze layer. Juno observes some of their effects as ripples, narrow bands, or repeated brightness patterns. Near the poles, the haze often follows the geometry of large cyclonic systems without belonging to the same pressure level. The underlying circulation can lift material and alter temperature above it. At the same time, auroral heating acts from higher altitudes. The polar haze therefore sits between two major sources of influence, one rising from below and one entering from above. Its structure records the combined result. The haze particles do not remain suspended forever. Gravity slowly pulls them downward. Some collide and grow larger, causing them to settle more quickly. Others evaporate when they reach warmer layers or react with surrounding gases. Continuous chemical production replaces part of the material that is lost. The visible veil is therefore maintained by a balance among formation, transport, growth, settling, and destruction. Seasonal change on Jupiter is limited because the planet's axis tilts only slightly. The amount of sunlight reaching each pole changes less dramatically than it does on Earth. Even so, Jupiter's long orbit around the Sun creates slow variations in illumination and temperature. Internal changes in auroral power and atmospheric circulation may produce stronger short-term differences than the seasons themselves. Juno's close polar views show that the stratosphere is not merely an empty gap above the clouds. It is a chemically active region filled with fine particles and gentle motion. Sunlight breaks simple gases apart. Auroral particles create additional reactions. Winds and waves move the products across latitude and altitude. Tiny particles scatter, light absorb heat, and form layered veils over the poles. Their quiet appearance conceals a continuing exchange of matter and energy across one of Jupiter's thinnest visible regions. At the level where Jupiter first becomes visible as a patterned globe, sunlight meets a dense field of clouds arranged into bright zones, dark belts, oval storms, narrow filaments, and long bands that circle the planet. This level is not a solid surface. It is a changing layer of gas and suspended particles near the pressure where the atmosphere becomes opaque to visible light. JunoCam records this region in reflected sunlight, revealing structures that appear familiar from distant telescopes, while also showing a finer texture that only close polar passes can resolve. The bright zones generally contain higher, thicker clouds. The darker belts expose deeper and warmer material through thinner cloud cover, though colour and brightness also depend on particle composition and illumination. The main visible cloud is thought to contain ammonia ice. At suitable temperatures, ammonia gas condenses into crystals that scatter sunlight. These crystals form broad sheets, compact cloud towers, and thin streaks pulled by the winds. Their altitude varies because temperature, pressure, and vertical motion are not uniform. Jupiter's bands run mainly from east to west. They are shaped by zonal winds, meaning winds that flow around the planet along lines of latitude. Adjacent jets move in opposite directions and create sharp boundaries between belts and zones. Some winds travel faster than 100 meters per second. JunoCam does not measure wind directly. Instead, images taken at different times allow cloud features to be tracked as they move. Their shifting positions reveal speed and direction near the visible cloud tops. The banded pattern becomes less orderly near the poles. At middle and low latitudes, the belts and zones form long, nearly parallel lanes. At high latitudes, the bands narrow, curve, and break into countless vortices. Juno's polar perspective shows a crowded field of small cyclones, anticyclones, filaments, and turbulent patches. The atmosphere there resembles a moving mosaic instead of simple stripes. The rapid rotation of the planet still influences every feature, but the geometry of the poles changes how that motion is organized. Cyclones are regions in which air rotates in the same general sense as the planet. Anticyclones rotate in the opposite sense. On Jupiter, both can persist for long periods because there is no solid ground to create strong friction. Their visible shapes depend on cloud altitude, temperature, and the motion of surrounding air. Some appear as compact spirals, others stretch into ovals or irregular patches. Thin cloud filaments wrap around their edges and mark the flow of gas. The largest anticyclonic system is the Great Red Spot. At the visible level, it appears as an oval enclosed by fast winds. Its colour changes with time from pale orange to deeper red. The cause of the colour remains uncertain. Observations indicate that compounds formed from ammonia and other trace gases may be altered by sunlight, creating reddish particles near the upper cloud layer. The colour is therefore likely connected to chemistry and exposure, rather than to a single deeply coloured substance rising from below. JunoCam images show that the Great Red Spot is not smooth. Its interior contains curved bands, small eddies, and regions of different brightness. Around its boundary, narrow streams of cloud move at high speed. Small vortices approach, stretch, and sometimes pass around the larger storm. The visible form changes continually, while the overall oval remains recognizable. Measurements over many decades show that the spot is gradually becoming smaller, although it still covers an area wider than Earth. Smaller white and brown ovals appear throughout the belts and zones. White ovals usually contain high bright clouds and often behave as anticyclones. Brown regions may reveal thinner clouds or different particles. Their colours do not define one simple altitude or composition in every case. The same shade can arise from several combinations of cloud thickness, sunlight, temperature, and chemical material. Scientists therefore compare colour with motion, infrared brightness, and surrounding structure. Juno also records long trains of waves. Some appear as repeated bright and dark crests arranged across a belt. Others form curved lines around vortices. Atmospheric waves carry energy through pressure, temperature, or wind changes without transporting the same parcel of gas over the full distance. They can begin when jets become unstable, when storms disturb nearby layers, or when air moves over regions of changing flow. Their wavelengths and orientations reveal how the surrounding atmosphere responds. At the equator, bright plumes rise into the upper visible clouds and spread westward or eastward into long tails. Darker regions between the plumes are often called hotspots because they emit more infrared energy. In visible light, they appear as gaps or thin places in the cloud cover. The repeating pattern of plumes and hotspots moves around the planet as a large atmospheric wave. The clouds within it change, but the broad arrangement can persist. Cloud shadows provide clues to vertical relief. When sunlight arrives at a low angle, tall cloud towers cast dark marks on lower decks. Juno Cam has recorded small bright clouds rising above their surroundings, especially in turbulent regions. Their shadows indicate that the visible atmosphere contains real height differences rather than a flat painted surface. Some towers may be produced by strong upward motion that carries ammonia ice to greater altitude before winds spread it into a bright cap. The polar regions contain large central cyclones surrounded by smaller circumpolar cyclones. In the north, several storms form a roughly organized ring around a central vortex. In the south, a different number forms another stable arrangement. Juno Cam and infrared observations show that these systems maintain distinct shapes, while shifting slightly and interacting at their boundaries. Their continued separation suggests that rotating flows can settle into a balanced pattern instead of merging immediately. Lighting changes the appearance of every cloud. Near the center of Jupiter's sunlit disk, sunlight reflects more directly toward the camera. Near the limb, the viewing path passes through a longer stretch of atmosphere, making high haze and thin cloud edges more visible. Juno's close approach creates extreme viewing angles and rapidly changing perspective. Image processing helps correct geometry and enhance faint differences, but the recorded structures remain tied to real variations in reflected light. Across repeated passages, the visible cloud tops show an atmosphere that is ordered and turbulent at the same time. Long jets maintain the planet's broad bands. Vortices bend and interrupt them. Waves cross belts and wrap around storms. Bright ammonia clouds rise, spread thin and dissolve. Colors change with chemistry, height, and illumination. Juno's images turn Jupiter's familiar striped appearance into a detailed record of motion across a deep fluid world. Within the cold upper part of Jupiter's weather system, Juno finds electrical storms in a place where ordinary liquid water should not remain stable. Earlier spacecraft detect lightning mainly as broad flashes shining through the cloud tops, and those observations support a simple picture. Water clouds lie far below the visible ammonia layer where pressure is greater, and temperatures are warm enough for water vapor, liquid droplets, and ice to exist together. Collisions among these forms separate electric charge, and the stored energy is released as lightning. Juno confirms that deep lightning still occurs, but it also detects a second kind of flash much higher in the atmosphere. The new flashes are small and faint. Juno's Stellar Reference Unit records them while the spacecraft looks across Jupiter's dark side. This camera is designed to detect dim stars for navigation, so it can also notice brief points of light against the unlit clouds. The apparent size of the flashes indicates that they do not shine upward through many tens of kilometers of dense cloud. They originate closer to the visible cloud tops within a shallower and colder storm region. At these heights, temperatures can fall below -80 degrees Celsius. Pure liquid water cannot persist under such conditions. Water lifted from deeper levels freezes into crystals, and without another substance, the familiar mixture of liquid droplets and ice would disappear. The shallow lightning therefore points to a different cloud chemistry. Juno's observations support a process in which ammonia changes the freezing behavior of water and allows electrically active liquid to form far above the main water cloud. Powerful thunderstorms begin deeper in the atmosphere where warm water-rich gas rises rapidly. As the gas expands into lower pressure, it cools. Water vapor condenses, freezes, and forms particles that are carried upward by strong currents. Some ice crystals rise more than 20 kilometers above the level where the main water cloud forms. They enter air that contains ammonia vapor from the upper atmosphere. Ammonia acts as an antifreeze. When it meets the rising water ice, it lowers the temperature at which part of that ice melts. A cold liquid solution of ammonia and water forms on or around the particles, even though the surrounding air is too cold for pure liquid water. The liquid does not create a broad, quiet cloud. It exists within turbulent storm towers where particles move upward and downward at different speeds. Falling droplets of ammonia-water solution collide with rising crystals of water ice. The collisions transfer electric charge from one particle population to another. Gravity and strong vertical winds then separate the charged particles. Some regions become more positively charged, while others become more negatively charged. As the electrical difference grows, the surrounding hydrogen-rich gas can no longer insulate the charges completely. A discharge passes through the cloud and produces a short flash. The word shallow describes the altitude of the electrical process, not the strength of Jupiter's storms. The thunder clouds that supply the ice begin much deeper, and their rising currents carry material through a large vertical distance. Only the final charge separation and discharge occur high above the ordinary water cloud. The visible flash therefore marks the upper part of a deep convective system. Juno finds many of these flashes at high latitudes. Jupiter's polar regions contain numerous cyclones and compact storms, and their broken cloud patterns allow the spacecraft to observe the night side at close range. The distribution differs from lightning on Earth, where the greatest activity is concentrated in warm tropical regions. On Jupiter, internal heat, rapid rotation, atmospheric composition, and polar circulation create a different arrangement of storm energy. Small bright clouds seen by JunoCam support the same picture. These compact features rise above their surroundings and sometimes cast shadows on lower clouds. They are often called pop-up clouds because they appear as bright towers emerging from a darker field. Their height and sharp form indicate vigorous upward motion. Some are likely the upper caps of storms that carry water ice into the ammonia-rich layer where shallow lightning develops. The same mixture that enables shallow lightning may also create unusual hailstones. Within the turbulent cloud, ammonia water liquid coats ice particles. Repeated movement through rising and falling currents adds new layers of slush and ice. The particles grow in a manner broadly similar to hail on Earth, but their composition is different. Researchers describe them as mush balls because their interiors contain a soft mixture of water and ammonia beneath a harder crust of water ice. A mushball can begin with an ammonia-rich liquid droplet or a small icy particle. It moves through regions containing water crystals and cold liquid. Material freezes onto its surface, melts partly in warmer pockets, and freezes again as the storm carries it through changing conditions. The outer ice shell becomes thicker, while the interior remains partly slushy. Growth continues until the updraft can no longer support the added mass. The heavy particle then falls. It carries ammonia and water away from the upper storm layer and into regions of greater pressure and temperature. During the descent, the outer shell melts, the slushy interior warms, and the material eventually evaporates. The released gases return to the atmosphere at a deeper level than the place where they first entered the storm. This process offers an explanation for part of the uneven ammonia distribution measured by Juno. Shallow lightning and mushballs remain connected parts of a scientific model rather than objects directly collected by the spacecraft. Juno observes the flashes, the cloud structures, and the microwave pattern of missing ammonia. Laboratory knowledge and atmospheric calculations show that ammonia water liquid can exist at the required temperatures. Together, these lines of evidence support the proposed cycle, although the exact sizes, lifetimes, and internal structures of individual mushballs remain uncertain. Within this cold storm region, Juno reveals weather that does not follow the simpler expectation of water clouds alone. Ice rises from depth, ammonia changes its melting point liquid solution, forms in intense turbulence, and collisions build separated electric charge. Brief flashes illuminate the upper clouds while growing hailstones carry volatile material downward. The shallow layer therefore acts as both an electrical zone and a transport system, quietly changing the composition of the atmosphere beneath Jupiter's visible surface. Beneath Jupiter's visible ammonia clouds, Juno finds that ammonia gas is not spread evenly through the atmosphere. Before the mission, many models treat the deeper weather layer as a place where strong mixing should smooth the composition. Ammonia is expected to condense near the upper clouds' fall as particles evaporate lower down and return upward through convection. Such a cycle should create predictable changes with altitude, while leaving the deeper atmosphere comparatively uniform. The microwave radiometer reveals a more complicated arrangement. Ammonia is a molecule made from nitrogen and hydrogen. Although it forms only a small fraction of Jupiter's atmosphere, it strongly absorbs microwave radiation at several of the wavelengths measured by Juno. Where ammonia is abundant, less microwave energy escapes from warm levels below. Where it is scarce, the instrument receives a brighter signal from greater depth. Temperature also affects the measured brightness, so the observations cannot be read as a direct picture of composition. Scientists compare all 6 microwave channels and use atmospheric models to separate the effects of temperature, pressure, and ammonia abundance. The 6 channels do not observe 6 thin, sharply divided layers. Each one receives radiation from a broad range of pressures, with its strongest sensitivity centered at a different depth. Shorter wavelengths are influenced mainly by the upper atmosphere, while longer wavelengths can emerge from much deeper levels. As Juno spins, the antennas sweep across Jupiter from limb to limb. Repeated passes produce long strips of microwave brightness, extending from northern to southern latitudes. The first measurements show a strong contrast between the equatorial region and most other latitudes. Near the equator, ammonia remains relatively abundant through a deep vertical column. The microwave pattern suggests that ammonia-rich gas rises there from below and continues upward toward the cloud-forming region. This broad equatorial plume is not a narrow storm tower. It extends across several degrees of latitude and persists through repeated observations, although smaller structures within it change. Away from the equator, much of the atmosphere is depleted in ammonia to surprising depths. The missing gas is not confined to the level where ammonia ice forms. In many regions, the depletion reaches far below the visible clouds, through pressures where condensed ammonia should already have evaporated. This depth makes simple ammonia snowfall insufficient as a complete explanation. Small ice crystals would warm and release their ammonia before carrying it so far downward. The pattern also varies with latitude. Some belts contain more ammonia at one depth and less at another. Some zones show the opposite behavior. The familiar bright and dark bands seen in visible light do not preserve the same contrast at every microwave wavelength. Their microwave appearance changes with depth, showing that the relationship between cloud color temperature and chemical composition is not fixed throughout the weather layer. At certain pressures, the contrast between belts and zones can even reverse. A region that appears microwave bright higher up may become darker below, while a neighboring region changes in the opposite direction. Scientists use this term jovicline for a broad transition where these microwave relationships shift. The name describes an observed boundary in atmospheric behavior rather than a solid surface. Its exact depth varies with latitude and with the assumptions used to interpret the radiometer data. Vertical circulation provides part of the explanation. Rising gas expands and cools, allowing ammonia to condense. Sinking gas compresses and warms, causing cloud particles to evaporate. If circulation consisted only of steady upward motion in zones and downward motion in belts, the ammonia pattern would be orderly. Juno instead sees narrow plumes, broad depleted areas, and changes that extend across several pressure levels. The atmosphere contains circulation cells of different sizes that overlap and interact. Large storms disturb this distribution. Strong updrafts carry water ice into the cold ammonia-rich region. Above the main water cloud, ammonia dissolves into liquid water created by the antifreeze effect described by the shallow lightning model. Collisions build ammonia-water hailstones or mushballs that become heavy enough to fall. These particles can carry both ammonia and water through levels where ordinary ammonia ice would evaporate. As a mushball descends, its outer shell warms and melts. The ammonia-water mixture eventually turns back into vapor, releasing its material at greater pressure. The storm has therefore moved ammonia downward without requiring the surrounding gas to sink by the same distance. Repeated storms can remove ammonia from broad upper regions and deposit it much lower. This process is consistent with Juno's observations, though the spacecraft does not directly detect individual mushballs. The atmosphere must later return some of that ammonia upward. Slow-mixing broad circulation and fresh convective plumes can transport gas from deeper levels. The equatorial region appears especially effective at maintaining an ammonia-rich upward path. At other latitudes, downward transport by precipitation may operate more strongly or more frequently than upward replacement. The observed pattern represents the balance of these processes over time. Microwave brightness also changes around individual vortices and turbulent regions. Some storms contain central areas with one ammonia pattern and surrounding rings with another. Rising and sinking motions can be arranged side by side across a single weather system. Juno's repeated passes reveal that these structures possess vertical organization even when their visible cloud tops show only part of the circulation. Interpreting the measurements remains difficult because temperature and ammonia both shape the signal. A warm layer with abundant ammonia can resemble a cooler layer with less ammonia at one wavelength. Using several channels reduces this uncertainty, but it does not remove it completely. Researchers compare microwave data with infrared temperatures visible, cloud motion, lightning locations, and atmospheric calculations. Different models can reproduce parts of the observations while assigning somewhat different values to the ammonia concentration. Even with these limits, the central result remains clear. Jupiter's atmosphere below the visible clouds is chemically uneven over great distances and substantial depths. Ammonia is concentrated in a broad equatorial column, depleted across many other latitudes, rearranged by belts and zones, and carried downward within powerful storms. Juno shows that composition is not merely a passive marker within the weather. Ammonia participates in clouds, lightning precipitation and circulation, while those same processes continually reshape where the molecule is found. Deeper beneath the ammonia-rich layers, Jupiter's atmosphere reaches temperatures and pressures where water becomes an important part of the weather. This region does not contain a single flat cloud sheet. It contains rising columns, sinking clearings, ice particles, liquid mixtures, vapor, and broad zones, in which the amount of water changes from place to place. Juno examines it with microwave radiation that passes through the visible clouds and with radio signals produced by lightning inside storms. Water is a minor ingredient compared with hydrogen and helium, but it carries unusual scientific importance. Oxygen is one of the most abundant heavy elements in the solar system, and most oxygen in Jupiter's deep atmosphere is expected to appear in water. Measuring water therefore helps estimate Jupiter's oxygen content. That abundance preserves information about the material from which the planet forms, although the connection depends on how solids and gases move through the early solar system. The upper boundary of the main water cloud lies several tens of kilometers below the visible ammonia deck. Pressure there is several times greater than the pressure at Earth's surface, and temperature rises with depth. Water vapor carried upward begins to condense as the gas expands and cools. Depending on local temperature, the condensed material appears as ice liquid droplets, or mixtures of both. Ammonia can dissolve into the water and change the exact freezing and condensation conditions. Strong convection gives this region much of its structure. Convection is the movement produced when warmer, less dense gas rises and cooler, denser gas sinks. Jupiter releases more heat than it receives from the Sun, so energy continually moves outward from the interior. In water-rich regions, condensation adds another source of upward power, because the change from vapor to liquid or ice releases heat into the surrounding gas. A growing storm begins where moist gas rises from greater pressure. Water condenses within the expanding column, forming dense clouds hidden from ordinary cameras. The rising current can become strong enough to carry ice far above the main condensation level. Around the updraft, cooler or drier gas descends. The storm therefore contains neighboring regions of cloud, clear air, rising motion, and sinking motion rather than one uniform tower. Lightning gives direct evidence that water participates in these deep storms. Charge separation works most efficiently when liquid droplets, ice crystals, and larger frozen particles collide in turbulent air. Small particles tend to move upward with the current while heavier particles fall. Their collisions transfer charge, and their separation creates a growing electrical difference. When that difference becomes large enough, a discharge crosses the hydrogen-rich gas and releases radio energy. Juno's microwave radiometer detects short radio pulses from lightning, even when the flashes remain hidden beneath thick clouds or occur on the sunlit side. Earlier observations already show that Jupiter produces powerful lightning, but Juno locates many events with improved sensitivity and spatial coverage. The deepest discharges are consistent with electrical activity near the main water cloud, where pure water can exist in several physical forms. The lightning distribution differs from Earth's pattern. Earth receives its strongest solar heating near the equator, where warm oceans and moist air support frequent thunderstorms. Jupiter receives much less sunlight, and its weak equatorial temperature contrast does not control convection in the same way. Internal heat escapes more easily at higher latitudes where sunlight adds less warming to the upper atmosphere. This arrangement helps make lightning common away from the equator, especially in turbulent northern and southern regions. Microwave measurements provide the broader estimate of water abundance. Water molecules absorb part of the natural microwave radiation rising from warmer depths. A wet atmosphere and a dry atmosphere therefore produce different brightness patterns, but temperature and ammonia also influence the signal. Scientists compare Juno's 6 microwave channels, each sensitive to a broad range of pressures, and construct models that reproduce the measured radiation. The equatorial region provides the clearest early result because its deep atmosphere appears more evenly mixed than many other latitudes. Juno's data indicate that water accounts for about 1/4% of the molecules there. When oxygen bound in water is compared with hydrogen, the abundance is roughly 3 to 4 times the corresponding solar value. The exact result depends on atmospheric assumptions, but it is clearly greater than the amount measured by the Galileo probe. The Galileo atmospheric probe enters Jupiter in December of 1995 and transmits for 57 minutes while descending. It reaches a pressure of about 22 bars and a depth near 120 kilometers below the level conventionally treated as the cloud tops. The water abundance remains unexpectedly low through much of the descent, and continues rising near the end without reaching a clearly uniform value. Later observations show that the probe enters a warm-dry feature called a hotspot. In such a region, gas sinks and warms, cloud formation weakens, and water vapor can be depleted across a large vertical distance. The probe's direct measurement is accurate for its path, but that path does not represent Jupiter as a whole. Juno avoids the limitation of a single entry point by measuring long tracks across many latitudes from orbit. The equatorial result does not yet provide a complete global average. Water can vary because storms lift it, precipitation carries it downward, and large circulation systems move moist and dry gas across latitude and depth. Microwave signals outside the equator are more difficult to interpret because ammonia and temperature are also strongly uneven. Observations establish that Jupiter is not uniformly dry, but the planet-wide oxygen abundance remains less certain than the equatorial value. Within the water-bearing cloud region, Juno replaces a simple dry picture with a moving and locally variable one. Hidden clouds form where moist gas cools. Deep lightning marks collisions among water particles. Clearings reveal sinking, drier air. Microwave radiation measures the combined effects of water, ammonia, pressure, and temperature. The region contains enough water to influence storm energy and chemistry, yet its distribution remains shaped by a circulation system that does not mix the entire planet evenly. Below the main water-bearing clouds, Jupiter does not become immediately calm or chemically uniform. Juno's microwave radiometer continues to receive natural radiation from warmer levels at greater pressure, and the measurements show that the active weather region extends well beneath the layers where ammonia and water condense. Temperature composition and vertical motion continue to vary across latitude. The atmosphere remains organized by rising and sinking gas, even where no visible cloud can mark the flow. This deeper region is difficult to describe by altitude alone because Jupiter has no solid surface from which height can be measured. Scientists instead use pressure. Pressure increases downward as more gas lies above each level. Near the visible cloud tops, the pressure is close to 1 bar. The longest microwave wavelengths used by Juno can receive information from regions approaching 100 bars under favorable conditions. These pressures correspond to depths of several hundred kilometers beneath the visible clouds, although the exact distance depends on temperature and atmospheric structure. Hydrogen and helium still make up nearly all of the gas. Water, ammonia, hydrogen sulfide, methane, and other trace substances remain present in much smaller amounts. At the temperatures found below the main cloud layers, most ammonia and water exist as vapor rather than as visible ice or droplets. Their molecules still absorb microwave energy, so they continue to influence what Juno measures. A cloudless layer is therefore not an empty or featureless layer. Heat rises through this region from Jupiter's interior. Warm gas expands and becomes less dense, encouraging upward motion. Cooler gas becomes denser and tends to sink. In a simple atmosphere, repeated convection might gradually mix temperature and composition until broad differences become small. Jupiter's rapid rotation and strong east-west circulation interrupt that simple process. They organize motion into band cells and barriers that limit how freely material crosses from one latitude to another. The microwave maps show that the bright zones and dark belts visible above do not end at the water clouds. Their thermal and chemical signatures continue downward, but they change character. At shallower microwave levels, many belts appear brighter than neighboring zones. Greater brightness can indicate warmer gas, lower ammonia abundance, or a combination of both. Deeper down, the contrast reverses across many latitudes and the zones become brighter than the belts. This reversal occurs near a broad transition roughly 65 kilometers below the expected water cloud level in many models. Researchers call it the Joviklen because its behavior resembles a boundary within a deep ocean, where temperature or composition changes across a limited vertical interval. The name does not imply that liquid water forms a global sea. It describes a change in the relationship among microwave brightness, atmospheric bands, temperature, and trace gases. Above this transition, familiar cloud-level processes strongly influence the microwave pattern. Ammonia condenses storms, move volatile material, and precipitation removes gases from some regions. Below it, condensation becomes less direct because the atmosphere is warmer. The continued belt zone contrast must depend more strongly on broad circulation temperature differences and the movement of vapor through the deep gas. Juno shows that meteorology continues after ordinary cloud formation becomes less important. The boundaries between bands can remain sharp at several microwave depths. Such sharpness indicates that horizontal mixing is incomplete. Gas on one side of a boundary can retain a different temperature or ammonia abundance from gas on the other side. Rapid east-west motion stretches these differences around the planet, producing long atmospheric lanes. Smaller disturbances blur parts of the boundaries, but they do not erase the global banded organization. Vertical motion also changes with latitude. Near the equator, ammonia-rich gas rises through a broad column and preserves a distinct microwave signature. At other latitudes, depleted regions suggest downward transport or precipitation, followed by slow replacement. Deeper measurements indicate that these patterns are connected to circulation, extending beyond the cloud-forming zones. The atmosphere carries chemical differences downward and upward, across distances much greater than the thickness of any single cloud layer. Temperature cannot be measured independently at every location with complete precision. Microwave brightness depends on both physical temperature and the abundance of absorbing gases. A warm region containing more ammonia can resemble a cooler region containing less ammonia. Juno's 6 channels reduce this ambiguity, because each wavelength responds differently to pressure and composition. Scientists also compare the microwave maps with infrared temperatures, gravity information, cloud motion, and atmospheric models. The resulting picture does not identify one exact lower edge for all weather. Different kinds of motion weaken at different depths. Small cloud processes end where condensation is no longer possible. Broad compositional patterns continue farther. Thermal contrast can persist where visible and infrared instruments cannot reach. The phrase weather layer therefore describes a region whose properties change gradually, rather than a shell with a sharp bottom. Energy moving upward through this region can travel by convection waves and large-scale circulation. Rising gas transports heat directly. Waves carry energy through repeated compression and expansion. Horizontal flows redistribute heat around latitude bands. Jupiter's fast rotation strongly turns moving gas so vertical and horizontal motions remain linked. The weather layer behaves as part of a rotating fluid rather than as a stack of independent atmospheric sheets. Juno's measurements also show that conditions differ between the equator middle latitudes and poles. No single microwave profile represents the entire planet. The equator is relatively rich in ammonia. Many middle latitude regions display alternating belt and zone signatures. High latitudes contain a crowded pattern of smaller contrasts. Repeated polar passes slowly improve coverage, but each measurement still records a changing atmosphere at one place and time. Below the water clouds, Jupiter remains a world of motion. Gas rises and sinks without producing a visible surface. Heat and trace molecules create microwave patterns that preserve the planet's bands. A broad transition changes the appearance of belts and zones with depth. Chemical differences survive despite vigorous circulation. Juno reveals an extended meteorological region in which clouds become less important, yet temperature composition and organized flow continue to shape the hidden atmosphere. Within Jupiter's extended weather layer, the largest vortices continue far below the clouds that make them visible. A vortex is a region of rotating fluid organized around a central area. From above, it appears as an oval spiral or compact swirl. Juno's microwave and gravity measurements show that these storms are not thin markings spread across the cloud tops. They possess vertical structure with changes in temperature and density reaching hundreds of kilometers into the atmosphere. The Great Red Spot provides the clearest example. It is an anticyclone, meaning that its circulation turns opposite to the direction expected for a cyclone in the same hemisphere. Its visible boundary is defined by fast winds that flow around a broad oval. Cloud filaments enter the surrounding current, stretch into long arcs, and pass around the storm. The interior contains slower regions, smaller eddies, and uneven cloud patterns. These details change while the larger circulation remains organized. Juno passes directly above the Great Red Spot during selected close approaches. JunoCam records the visible structure while the microwave radiometer measures radiation emerging from levels hidden beneath it. Each microwave channel responds most strongly to a different range of pressure. By comparing the channels, scientists trace how the storm's temperature and ammonia pattern change downward. The signal remains distinct well below the expected water cloud region. The microwave observations indicate that the Great Red Spot extends more than 350 kilometers beneath the visible cloud tops. Its deeper boundary is not a solid base. The temperature and composition differences gradually weaken until the surrounding atmosphere becomes difficult to distinguish from the storm. Depending on the wavelength model and definition used, the detectable structure can reach several hundred kilometers. The measurement therefore describes a broad route rather than a sharply bounded column. Gravity provides a second method. Any large atmospheric structure contains small differences in density and mass. As Juno flies over such a region, the additional gravitational pull changes the spacecraft's speed by a tiny amount. Radio signals sent between Juno and Earth reveal this change through a slight shift in frequency. Two low passes over the Great Red Spot allow scientists to isolate part of its gravity signature from the much stronger pull of Jupiter as a whole. The measured signal constrains the characteristic depth of the Great Red Spot to roughly 300 kilometers. This result agrees broadly with the microwave evidence, although the two techniques respond to different properties. Microwave measurements follow temperature and absorbing gases. Gravity measurements respond to the distribution of mass. Their agreement shows that the visible storm is connected to a deep density structure rather than to a shallow color pattern alone. The depth is small compared with Jupiter's radius, yet it is large compared with familiar weather systems on Earth. Earth's strongest storms occupy only a thin part of the atmosphere above a solid surface. Jupiter has no nearby ground beneath the vortex, so friction does not weaken it in the same way. The surrounding gas continues downward, allowing the rotating structure to extend through pressures and temperatures far beyond those at the cloud tops. The internal temperature pattern also changes with vortex type. Juno's microwave observations show that many cyclones are warmer near their upper parts and colder below. Anticyclones show the opposite arrangement, with colder upper regions and warmer material at greater depth. These contrasts correspond to differences in density. Warm gas is generally less dense at the same pressure, while cold gas is denser. The exact relationship is altered by composition and motion, but the broad pattern helps reveal the storm's vertical circulation. In an anticyclone, such as the Great Red Spot, air near the upper visible region tends to spread outward and descend around parts of the structure. Expansion and cooling help produce a cold upper signature. At greater depth, compressed or slowly sinking gas can appear warmer. The circulation is not a single simple loop, and local motions vary around the oval. Still, the measured temperature reversal is consistent with the storm, whose rotating pressure system reaches downward through a substantial column. Smaller vortices also possess deep roots. Some extend approximately 100 kilometers below the clouds, while larger systems reach farther. Their depths do not scale perfectly with visible width. A broad storm can be relatively shallow, and a more compact one can preserve a strong microwave signature at depth. Rotation speed, surrounding winds, temperature contrast age, and interaction with neighboring structures all influence the vertical form. At the poles, groups of large cyclones remain arranged around central storms. The northern group forms an approximately octagonal pattern, while the southern group forms an approximately pentagonal pattern. Infrared measurements show that the storms oscillate slightly around balanced positions rather than merging into one vortex. Each cyclone pulls on its neighbors through the surrounding flow. The central cyclone also affects their motion and helps prevent them from moving directly over the pole. Their stability indicates that the polar cyclones are more than temporary cloud features. Deep roots give them inertia and allow each storm to influence a large volume of gas. The surrounding vortices push and pull one another, producing slow movements around equilibrium positions. Differences in storm size and spacing help maintain the distinct northern and southern arrangements. The exact depth of every polar cyclone remains uncertain, but their persistence and thermal structure indicate substantial vertical extent. The Great Red Spot also changes over time despite its depth. Its visible width has decreased during modern observations and its shape has become more circular. Flakes of red cloud sometimes peel away when smaller vortices pass nearby, but these events do not necessarily represent the loss of the deeper circulation. Color cloud material and the underlying wind field can change at different rates. The visible edge is therefore not identical to the full dynamical boundary. The deep root changes how the storm responds to its surroundings. A passing vortex can disturb upper clouds quickly, while the deeper mass adjusts more slowly. Momentum remains distributed through a tall rotating column, and pressure differences stay connected across many levels. This vertical continuity helps the storm preserve its identity, even as filaments stretch, colors fade, and smaller eddies enter its boundary. Beneath the visible oval, the circulation remains embedded in dense hydrogen, where gradual changes in temperature and density carry the structure downward until it blends into the surrounding atmosphere. At the depths where individual storms begin to fade into the surrounding atmosphere, Jupiter's broad east-west winds remain detectable. These winds form the belts and zones that encircle the planet. At the cloud tops, alternating jets carry gas eastward and westward at different speeds. Juno's gravity measurements show that this striped circulation is not confined to the visible weather. It continues downward through roughly 3,000 kilometers of hydrogen-rich material involving a mass far greater than the clouds alone. A zonal jet is a current that flows mainly along latitude. Jupiter contains many such jets in each hemisphere, Some move in the direction of the planet's rotation, while neighbouring jets move more slowly or in the opposite direction relative to the deep interior. The boundaries between them produce wind shear, which is a change in speed or direction across a short distance. This shear stretches clouds into long bands and helps organize vortices, waves, and turbulent structures. Visible images reveal the speed of the cloud-top winds by tracking small features over time. They show rapid eastward jets near some zone boundaries and westward flow near others. Images alone cannot determine how far the currents continue below the clouds. The deeper gas becomes opaque to visible and infrared light, and no solid surface marks the lower edge of the flow. Juno therefore uses Jupiter's gravitational pull to detect the hidden motion. A rotating planet with perfectly even layers would produce a gravity field that is nearly symmetrical between north and south. Jupiter is flattened at the poles because of its rapid rotation, and this shape creates large, predictable gravity signals. Deep winds add smaller irregularities. The northern and southern jet patterns are similar but not exact mirror images. If those asymmetric winds carry dense gas far below the clouds, they shift small amounts of mass and create a measurable north-south difference in the gravity field. During close passes, radio signals travel between Juno and Earth. Jupiter's gravity changes the spacecraft's speed along its path, and the resulting frequency shift reveals the strength of the pull. The dominant signal comes from the planet's total mass and rotational flattening. Scientists remove these larger effects through mathematical models. What remains includes small gravity components associated with uneven internal structure and atmospheric flow. The gravity field is described through coefficients that represent different patterns in the distribution of mass. Some coefficients describe shapes that are symmetrical across the equator. Others describe north-south asymmetry. Before Juno, the odd gravity coefficients linked to that asymmetry remain poorly known. Juno measures them accurately enough to show that they match the expected influence of the observed zonal winds extending downward. Researchers compare the gravity measurements with models in which the cloud-top winds weaken at different rates with depth. If the jets remain strong too far inward, the predicted gravity asymmetry becomes larger than Juno observes. If they fade too quickly, the predicted signal becomes too small. The best agreement occurs when the main east-west currents continue for about 3,000 kilometers and then decline substantially. This depth is only a small fraction of Jupiter's radius, but it contains about 1% of the planet's total mass. The weather therefore involves an immense quantity of material. The jets are not thin surface streams sliding over an inactive sphere. They are broad-moving volumes embedded in the outer part of the planet where pressure and density rise continuously downward. The bands do not all have identical routes. Strong jets leave clearer gravity signatures than weak ones, and their decay with depth may differ by latitude. The equatorial jet is especially broad and powerful. Middle latitude jets are narrower and alternate more frequently. Near the poles, the orderly banded pattern gives way to smaller vortices and less regular flow. Gravity measurements provide a global constraint, so they describe the combined depth of the system more securely than the exact lower boundary of every individual jet. The deep currents also preserve the north-south differences seen near the clouds. This connection indicates that the visible winds are tied to the mass flow below, rather than being detached patterns maintained only in a shallow layer. Cloud colors and local storms can change quickly, but the underlying zonal organization persists because momentum is distributed through a much deeper column. Jupiter's rapid rotation strongly shapes these currents. Gas moving northward or southward is turned into east-west motion by the Coriolis effect, which is the apparent deflection created within a rotating system. The effect becomes powerful because Jupiter completes a rotation in less than 10 hours. Broad convection rising from the warm interior is redirected into zonal flow, and neighboring jets develop with opposite relative motion. Once established, the jets limit mixing across latitude. Material travels rapidly around the planet but crosses more slowly from one band to another. This helps maintain differences in ammonia temperature, cloud thickness, and color. Turbulence and vortices still exchange material across boundaries, yet the jets repeatedly stretch disturbances eastward and preserve the larger striped arrangement. The energy sustaining the currents comes from Jupiter's internal heat and from the redistribution of momentum within the atmosphere. Sunlight influences the upper clouds, but it supplies less energy than Jupiter releases from within. Rising and sinking gas feed motion while waves and eddies transfer momentum between jets. The exact balance varies with depth and latitude, and observations do not isolate one process as the sole cause of every band. At approximately 3,000 kilometers below the cloud tops, the winds become much weaker. Pressure has increased greatly. Hydrogen is denser, and electrical conductivity begins to rise. Motion relative to the deep interior becomes harder to maintain. The gravity signal shows a transition from a rapidly banded outer region toward a more uniformly rotating interior, though the decline is gradual rather than a sharp boundary. Juno's measurements give the visible belts a hidden dimension. Each bright zone and darker belt belongs to a circulation system whose east-west motion penetrates through thousands of kilometers of gas. The cloud tops display only the upper texture of these flows. Beneath them, enormous moving columns carry heat composition and momentum around the planet until their differing speeds weaken within the dense interior. The deep belts and zones do not descend toward Jupiter's center as straight radial sheets. Juno's refined gravity measurements indicate that the principal east-west winds follow a geometry created by rapid rotation. As the currents extend beneath the clouds, they align approximately parallel to the planet's rotation axis. In a cross-section through Jupiter, the moving regions resemble nested cylinders wrapped around that invisible axis, with each cylinder intersecting the cloud layer at a particular latitude. This arrangement differs from the pattern suggested by the visible surface. A cloud-top jet appears to circle Jupiter along one latitude. It is natural to imagine that its deeper part remains directly beneath that same line, becoming a vertical wall directed toward the center. On a rapidly rotating fluid planet, however, motion is constrained by the tendency of large flows to remain similar along lines parallel to the spin axis. The deeper portion of a jet therefore shifts in latitude as the curved outer surface narrows inward. A jet observed at 21 degrees north near the cloud tops illustrates the geometry. At a depth of roughly 3,000 kilometers, the same cylindrical flow intersects a level corresponding to about 13 degrees north. The current has not bent toward the equator in the ordinary sense. Its axis-parallel alignment remains nearly unchanged, while Jupiter's spherical surface curves around it. Latitude changes because the same cylinder crosses different spherical shells at different positions. The physical tendency behind this structure is often described through the Taylor-Proudman principle. In a fluid that rotates rapidly and changes slowly, broad motion tends to vary little along the direction of the rotation axis. Jupiter does not satisfy every condition of the simplest principle. Its gas is compressible, density rises strongly with depth, heat moves through convection, and magnetic forces become important below the weather layer. Even so, rapid rotation is strong enough to impose an approximately columnar form on the large zonal currents. These columns are not solid tubes with sharp walls. Each one is a broad region in which east-west speed changes gradually across latitude and depth. Neighbouring cylinders can rotate at different rates relative to Jupiter's deep interior. Their boundaries correspond to zones of strong wind shear, turbulence, waves, vortices, and smaller convective motions pass through and around them, so the cylindrical pattern describes the average organisation of the flow rather than every local movement. Juno identifies this geometry through the detailed shape of Jupiter's gravity field. The earlier gravity result establishes that cloud-level winds penetrate about 3,000 kilometers. Later analysis uses additional close passes and improved measurements of the gravity coefficients to test how those winds are arranged within the planet. Models based on radial descent and models based on axis parallel cylinders place moving mass in different locations. Each arrangement produces a slightly different gravitational pull on the spacecraft. The cylindrical models provide the closer match. They reproduce both the north-south asymmetry associated with the observed cloud winds and subtler symmetrical parts of the gravity field. This agreement does not create a direct image of every current. It identifies the geometry that best accounts for the measured mass distribution when combined with the known wind speeds at the cloud tops. Density increases greatly through the 3,000-kilometer wind layer. A small speed difference deep below the clouds moves more mass than the same difference in the thin upper atmosphere. For this reason, gravity measurements are especially sensitive to the lower portions of the jets. The data constrain how rapidly the winds weaken with depth, and how their cylindrical surfaces pass through increasingly dense hydrogen. The equatorial current requires special treatment, because a cylinder close to the rotation axis intersects a wide region around the equator. Jupiter's strong eastward equatorial jet occupies a broad band at the clouds and remains influenced by the symmetry of the rotating planet. Its deep form cannot be represented simply as a narrow column. Models allow its speed and width to change while preserving the general axis-parallel organization demanded by the gravity data. At higher latitudes, the cylinders lie farther from the rotation axis and intersect less of the deep planet. Their geometry produces narrower surface bands. Moving inward along one of these columns leads toward lower apparent latitude while its distance from the spin axis stays nearly constant. The alternating jets therefore form a set of nested shells around the axis, rather than layers following Jupiter's curved outer boundary. This structure helps explain why rapid rotation dominates the weather pattern. Rising and sinking gas may begin with motion directed partly outward or inward. The Coriolis effect redirects much of that movement into east-west flow. Convective eddies transfer momentum between neighbouring regions, strengthening some jets and weakening others. Once broad currents develop rotation, encourages them to retain coherence along the spin axis. The columns remain embedded in a spherical planet whose pressure density, temperature, and electrical properties change with depth. Their speeds are not constant from top to bottom. Gravity models indicate a gradual decay through the outer few thousand kilometers. The strongest cloud-level winds leave the clearest deep signature, while weaker currents become difficult to distinguish. The exact decay profile of each jet remains uncertain, because several different smooth profiles can fit parts of the gravity data. The cylindrical result describes an average state over the period of Juno's measurements. Cloud-top winds can vary, storms can exchange momentum with nearby jets, and waves can temporarily alter local speeds. The deep mass involved in a cylinder responds more slowly than individual cloud features. Short-lived changes at the visible level therefore do not necessarily extend through the entire column. Within this region, Jupiter's familiar stripes become the outer intersections of a deeper rotating framework. Each major jet follows a broad surface arranged around the spin axis. The surface latitude changes with depth because the planet is spherical, while the flow remains approximately columnar. Juno's gravity measurements reveal this hidden geometry by sensing where moving dense gas slightly shifts the planet's pull, turning the visible bands into nested currents, extending through the outer interior. Near the lower edge of Jupiter's deep wind system, the alternating eastward and westward jets lose much of their motion relative to the planet's interior. Juno's gravity measurements show that the main zonal currents extend through roughly 3,000 kilometers of gas, but they do not continue unchanged toward the center. Their speeds decline across a broad transition. Beneath this region, most of the dense planet rotates much more nearly as one body without the strong latitude by latitude differences that shape the visible atmosphere. Uniform rotation does not mean that every parcel of hydrogen remains perfectly fixed beside every other parcel. Convection waves and smaller motions continue within the fluid. The term describes the average angular speed of the deeper material. Angular speed is the rate at which matter turns around the rotation axis. In the weather layer, neighboring jets possess different angular speeds. Below the wind transition, those large differences become small enough that gravity measurements no longer require a strongly banded flow. The weakening begins where pressure and density have risen enormously above cloud level values. A moving parcel at this depth carries much more mass than a similar volume near the visible clouds. Even modest deep winds would therefore create a noticeable redistribution of mass and a measurable gravity signal. Because Juno detects only a limited contribution from such motion, the deep jets must lose strength before reaching far into the interior. The decline is not represented as a hard surface. No solid boundary separates fast weather from quiet interior rotation. Models that fit Juno's gravity field use smooth profiles in which wind speed decreases over hundreds or thousands of kilometers. The precise shape of the decrease remains uncertain. Some solutions allow a gradual fading, while others include a more concentrated breaking region. All successful models require the strong cloud top pattern to become greatly reduced below its measured depth. Several physical processes can oppose the jets. One possible process is magnetic drag. Hydrogen is electrically neutral through much of the upper atmosphere, but increasing temperature and pressure allow a small fraction of particles to carry electric charge. When electrically conducting fluid moves across Jupiter's magnetic field, it generates currents. Those currents interact with the field and produce forces that resist motion relative to the deeper planet. The effect resembles a brake, though no solid parts touch. Kinetic energy from the winds is converted partly into electrical energy and then into heat. This conversion is called ohmic dissipation. If powerful jets entered regions of high conductivity without weakening, they could generate more heat than Jupiter is observed to release. Energy limits therefore provide an independent reason for the winds to decline near the depths inferred from gravity. Magnetic drag may not act alone. The atmosphere also becomes strongly stratified in density as it descends. Stratification means that material of different density occupies different levels and resists vertical displacement. In a freely convecting region, rising and sinking gas can transport momentum and help maintain deep jets. In a stable layer, vertical motion is suppressed, so the exchange that supports the currents becomes less effective. A stable interval could therefore weaken the connection between the weather layer and the more uniformly rotating material beneath it. The origin and location of any stable layer remain uncertain. Changes in composition can create density differences. Heat can also move through radiation more efficiently within some pressure ranges, reducing convection. Models test these possibilities, but Juno's gravity data do not identify one unique cause. They reveal the depth and broad decline of the winds more directly than the mechanism that stops them. Large density changes alone can also alter the flow. As hydrogen becomes denser, a current must move increasing mass to preserve the same speed. The energy required becomes greater, while turbulence and waves redistribute momentum. Friction, in an ordinary molecular sense, remains weak, but many small interactions can transfer energy from organized jets into less ordered motion. The jets can therefore fade without meeting a physical flaw. The cylindrical geometry of the winds influences their braking. Each current remains approximately aligned with the rotation axis as it descends. Because density and conductivity vary with depth, different parts of a cylinder encounter different conditions. The resulting resistance may not be uniform along the full column. This uneven braking can change the shape of the flow before its speed becomes too small for Juno to detect. The transition must also conserve angular momentum. Angular momentum describes the rotational motion of mass around an axis. When a jet slows, its momentum does not simply disappear. It is transferred to neighboring fluid carried by waves redistributed by turbulence or converted through magnetic interactions. The deeper interior contains so much mass that receiving momentum from the weather layer changes its average rotation only slightly. Jupiter's measured rotation is commonly tied to the repeating radio signal associated with its magnetic field. This period represents the deep interior more reliably than visible cloud motion, because clouds travel eastward or westward at different rates. Juno's gravity analysis uses this deep rotation as the reference state. Wind speed then describes how quickly an atmospheric region moves relative to that underlying rotation. Near the cloud tops, the differences are large and form many distinct jets. At increasing depth, the differences shrink. The broad equatorial current, strong middle latitude bands, and weaker high latitude flows all contribute to the gravity pattern, yet none remains at full strength indefinitely. Their fading creates a gradual passage from differential rotation to near uniform rotation. Juno does not directly enter this region. Its evidence comes from the slight pull of moving mass combined with the measured cloud winds and models of Jupiter's density. These methods cannot trace every eddy or determine an exact braking altitude at every latitude. They establish a global constraint. The banded circulation occupies the outer portion of the planet, while the much larger mass below turns almost together. The lower boundary of the weather layer is therefore defined by motion rather than by a change in appearance. No cloud marks it and no simple chemical surface lies across it. The defining feature is the loss of strong east-west speed differences. Dense hydrogen, rising conductivity, possible stable layering waves, and turbulent momentum exchange all contribute to a gradual quieting. What remains is a vast rotating interior whose large-scale motion stays closely coupled while the vigorous jets above become a comparatively thin outer system. Below the region where the zonal winds fade, hydrogen enters a state in which it can carry electrical current through the deep interior. Pressure rises to millions of times the pressure at Earth's surface, while temperature reaches thousands of degrees Celsius. Under these conditions, hydrogen no longer behaves as the familiar transparent gas found in the upper atmosphere. Its molecules are compressed so closely that their electrons become increasingly free to move. The material remains fluid, but its electrical behavior begins to resemble that of a metal. This state is called metallic hydrogen. The change does not occur at one perfectly sharp surface. Molecular hydrogen gradually becomes a dense conducting fluid as pressure and temperature increase. Some models place a transition region above the more strongly metallic interior where conductivity grows over a substantial depth. Juno does not sample this material directly. Its magnetometers measure the field outside Jupiter, and scientists use those measurements with laboratory physics and interior models to infer the conditions that produce it. Electrical conductivity allows moving hydrogen to generate currents. Jupiter also rotates rapidly, completing one turn in a little less than 10 hours. Heat escaping from deeper levels drives slow convection through parts of the conducting fluid. Convection is the transport produced when warmer material rises and cooler material sinks. Rotation bends and organizes these motions into broad columns and swirling paths. The moving conductor creates electrical currents, and those currents generate a magnetic field. This self-sustaining process is called a dynamo. The dynamo does not operate like a permanent bar magnet hidden inside the planet. Its field is maintained by continuous motion. Electrical currents create magnetic forces, and those forces act back on the flowing hydrogen. Heat rotation density, conductivity, and magnetic resistance remain linked. When the balance changes, the pattern of the field can change as well, although the enormous scale of the interior makes most changes slow. Before Juno arrives, measurements from earlier spacecraft show that Jupiter possesses a powerful field with a strong dipole component. A dipole is the broad two-pole pattern familiar from a simple magnet. Models therefore often represent Jupiter's field as a tilted dipole, with smaller irregular features added to it. Juno's close polar passes reveal that those smaller features are not minor details. The field is unusually uneven across longitude and latitude. In parts of the northern hemisphere, strong magnetic flux emerges through compact regions. Magnetic flux describes the amount of magnetic field passing through an area. Some northern areas contain narrow zones of intense field beside much weaker surroundings. Across much of the southern hemisphere, the field is smoother and more broadly distributed. This north-south difference shows that the dynamo does not produce a simple symmetrical pattern. The measured strength also changes sharply along Juno's path. Close to some northern regions, the field becomes far stronger than older global models predict, while neighboring areas are weaker. Such variation reflects the combined effect of deep currents and the distance between each source pattern and the spacecraft. A compact source leaves a steep local signature. A broad source produces a smoother field. These differences allow magnetic mapping to provide limited information about structure far below the level reached by atmospheric measurements. One of the most distinct features lies near the equator. It is known as the Great Blue Spot because blue is used to mark inward-directed magnetic field on scientific maps. It has no visible color and no relation to the Great Red Spot. The feature is a concentrated magnetic region where field lines enter Jupiter. Juno follows its position and strength across repeated passes, allowing changes in the deep field to be compared over time. The Great Blue Spot drifts slowly eastward relative to Jupiter's standard interior rotation. Parts of its field also vary over several years. These changes are called secular variation, meaning a gradual change in a planet's magnetic field. Juno's observations indicate that motion within the conducting interior shifts the magnetic pattern. Recent analysis also identifies a roughly 4-year fluctuation associated with an equatorial flow consistent with an oscillating motion inside metallic hydrogen. The exact form of that hidden motion remains uncertain. The irregular map constrains the depth of the dynamo. Small magnetic structures fade rapidly with distance from their source, while large structures remain detectable farther away. Because Juno measures compact and uneven features close to Jupiter, the source cannot lie only in a very small central region. Magnetic models place the top of the main dynamo at about 4/5 of Jupiter's radius from the center. Beneath that level, convection within metallic hydrogen appears able to maintain most of the observed field. A layer influenced by helium may help define the upper boundary. At certain pressures and temperatures, helium becomes less soluble in metallic hydrogen and separates into droplets. The droplets sink through the surrounding fluid, a process commonly called helium rain. Changes in composition can make a layer more stable against convection. If vertical motion becomes weaker, the layer can filter or reshape magnetic structures rising from the deeper dynamo. The existence, thickness, and exact position of this stable region remain uncertain. Some magnetic models place it above the main dynamo and use it to explain the contrast between Jupiter's broad dipole and its local irregularities. Other models allow shallower conducting flows to modify the field. The remaining equatorial jet may reach material conductive enough to create additional magnetic features without generating the entire planetary field. Juno's magnetometers measure both field strength and direction during each close passage. Star cameras determine the exact orientation of the sensors, while spacecraft tracking establishes position. Repeated paths gradually build a global map. The measurements separate the internal field from magnetic effects produced by currents outside the planet. This distinction is essential because Jupiter's magnetosphere also creates powerful and changing fields around the spacecraft. The final magnetic map shows a deep fluid region rather than a simple hidden magnet. Metallic hydrogen conducts electricity. Convection and rotation organize its motion. Electrical currents maintain a strong global field, while local flows create concentrated patches and slow changes. Helium separation and rising conductivity may divide the region into layers with different kinds of motion. Juno cannot see the fluid directly, but the field reaching space preserves the shape and movement of the dynamo operating within Jupiter's electrically conducting interior. At Jupiter's deepest levels, the distinction between atmosphere and interior has disappeared. Hydrogen and helium remain the dominant materials, but the proportion of heavier substances increases toward the center. In planetary science, heavy elements means every element heavier than hydrogen and helium. These materials include oxygen, carbon, nitrogen, sulfur, silicon, iron, and other components associated with rock ice and complex compounds. Juno's gravity measurements indicate that much of this material is not confined inside a small, sharply separated central body. It is distributed through a broad inner region known as a dilute core. Before Juno, a common model gives Jupiter a compact core surrounded by a nearly uniform envelope of hydrogen and helium. The core may contain rock and ice accumulated during the earlier stages of planet formation, while the surrounding gas is added rapidly afterward. This picture remains physically possible in a general sense, but Juno's precise gravity field cannot be explained well by the simplest version of a small dense center and a fully mixed outer envelope. Juno measures the deep structure indirectly. During close passages, Jupiter's gravity accelerates the spacecraft. Radio tracking records tiny changes in Juno's motion, allowing scientists to map small departures from a perfectly smooth gravitational field. The planet's rapid rotation and flattened shape produce the strongest variations. Deep winds contribute additional signals. After these effects are modeled, the remaining gravity pattern constrains how density changes from the outer layers toward the center. Density depends on pressure, temperature, and composition. Hydrogen becomes denser as it is compressed, so gravity alone cannot identify a particular material at one depth. Researchers combine Juno's measurements with laboratory experiments and theoretical calculations, describing hydrogen, helium, water, rock-forming compounds, and mixtures under extreme conditions. They construct many possible interiors and retain the ones that match Jupiter's mass, radius, rotation, gravity field, and atmospheric composition. The successful models generally require an inner region enriched in heavy elements, but mixed with substantial hydrogen and helium. This region does not possess a simple edge. Heavy element concentration rises gradually inward across a large fraction of the planet. Some models place the dilute core through roughly the inner half of Jupiter's radius, while others produce a narrower or broader distribution. The exact extent depends on assumptions about temperature, material behavior, helium separation, and the depth of remaining internal flows. A dilute core is not dilute in the ordinary sense of being thin or unimportant. It may contain many times Earth's mass in heavy material. The word describes the spreading of that material through lighter fluid, instead of its confinement within a compact sphere. Near the center, the mixture can still be much richer in rock and ice-forming elements than the outer envelope. Moving outward, the heavy element fraction gradually declines until hydrogen and helium dominate more completely. Juno's data do not rule out a smaller compact core at the very center. A dense central region may remain beneath the broad enriched mixture. Its possible mass and size vary widely among models, and some acceptable solutions contain little or no sharply defined compact body. Gravity measurements respond to the combined density of many layers, so different internal arrangements can sometimes produce similar external fields. The existence of the dilute region is more secure than the detailed form of its innermost part. Pressure near Jupiter's center reaches tens of millions of bars and temperature reaches many thousands of degrees Celsius. Under such conditions, familiar labels such as rock ice, liquid, and solid become imperfect. Water and silicate materials may dissolve or mix into metallic hydrogen. Atoms and electrons interact within dense fluids whose behavior cannot be reproduced fully in ordinary laboratories. The central mixture is therefore not expected to resemble a cold, rocky surface hidden beneath gas. The gradual composition change can affect convection. A warm parcel usually rises if it is less dense than its surroundings, but a parcel containing more heavy material may remain dense even when heated. A composition gradient can therefore slow vertical mixing. Heat may still move outward through layered convection diffusion or slow overturning, while heavy elements remain concentrated toward the center. This resistance to complete mixing helps preserve a dilute core over billions of years. Several histories can produce such a structure. Jupiter may grow while solids dissolve progressively into its expanding envelope, creating an enriched central region from the beginning. A compact early core may partly erode as hot metallic hydrogen dissolves its material and carries it outward. A large collision during the young planet's formation may also mix an original core into the surrounding interior. Observations indicate a broad distribution of heavy elements, but they do not identify one unique history. The amount and placement of heavy material influence Jupiter's entire formation record. A planet that gathers small pebbles, larger planetesimals, or gas-containing vaporized solids can develop different composition profiles. The timing of rapid gas capture also matters. Material added early can sink or dissolve deeply, while material arriving later may remain closer to the outer envelope. Juno's gravity field preserves the final density pattern, but many earlier processes can lead toward a similar present structure. Helium separation may continue to alter the inner planet. Where helium becomes less soluble in metallic hydrogen droplets can form and sink. This movement releases gravitational energy and changes composition at different depths. It may also interact with the heavy element gradient and with regions of stable layering. Interior models include these effects in different ways, adding uncertainty to estimates of the core's exact mass and boundary. Juno's central discovery is therefore a change in form rather than the detection of a solid object. Jupiter's deepest structure is not well represented by a small hard sphere beneath a uniform gaseous envelope. The gravity field points instead to a wide central domain in which heavy elements blend gradually with compressed hydrogen and helium. A compact center may exist inside it, but its properties remain uncertain. At the heart of Jupiter, pressure, heat mixing and composition create a broad transition whose hidden mass shapes the gravity measured far above the clouds. Jupiter remains a planet without a visible boundary between sky and interior. The bright clouds form only the upper expression of a much deeper system. Above them, charged particles move through magnetic fields and pour energy into the polar atmosphere. Thin hazes gather where sunlight and chemistry create suspended particles. Ammonia clouds drift through powerful winds, while lightning flashes inside storms that carry water and ammonia across great vertical distances. Farther down, the atmosphere stays active long after ordinary clouds disappear. Microwave measurements reveal uneven composition and hidden circulation beneath the visible weather. Giant vortices extend hundreds of kilometers downward, while the broad belts and zones continue through several thousand kilometers of dense hydrogen. Their motion slowly weakens as the interior becomes more electrically conducting and begins to rotate more nearly as a single body. Deeper still, metallic hydrogen carries electrical currents through a hot compressed fluid. Convection and rapid rotation maintain Jupiter's magnetic field, creating a structure that is strong, irregular, and slowly changing. Beneath that dynamo lies a broad central region enriched in heavier material. Juno's gravity measurements indicate that this inner structure is not simply a small solid core surrounded by uniform gas. Heavy elements appear to spread gradually through a large fraction of the deepest planet. Juno never touches these hidden regions. It remains above the clouds, measuring gravity, radiation particles, magnetic fields, heat, light, and microwaves. From those distant signals, Jupiter becomes less like a painted sphere and more like a continuous fluid world, changing slowly from thin upper atmosphere to storms, deep winds, conducting hydrogen and a diffuse central interior. The clouds remain in motion above it all, concealing nearly everything beneath them.